Right. Okay. Hello, everyone. Hope you're all having a lovely afternoon, and a big welcome to the first NPPS seminar of the semester. We're very excited and fortunate to be joined by Professor Davide Costanzo. Professor Costanzo is currently a professor of experimental particle physics at the University of Sheffield, and over the years, he has also made significant contributions to the ATLAS experiment, the largest general purpose experiment at the LHC. So this includes, and is certainly not limited to, being the chairman of the ATLAS Authorship Committee, the coordinator of the ATLAS Upgrade Software, and the chairperson of the Physics and Software Validation Group. And currently, he is the team leader of the Sheffield ATLAS Group. Professor Costanzo's research focuses on two of the most important and well-known problems in physics, being the nature of dark matter and the fine-tuning problem of the Standard Model. His seminar today explores the first of these problems, giving a review of the search for one of the main candidates for dark matter and demonstrating the exciting future of physics at the ATLAS experiment. So before we begin, you will have the opportunity to ask questions. So if you do have any, feel free to pop them in the group chat or just wait at the end and you'll have the opportunity to ask yourselves. I think that's it. So without further ado, I'll hand over to Professor Costanzo.
Right.
Thank you.
Thank you. Can you still hear me? Yeah.
Yep.
Right. Brilliant. All right. So I'll get started. So, so first of all, there you go. Yeah. Thanks a lot for inviting me. For obvious reasons, I didn't manage to make the trip over to Manchester, so I decided to put a picture, which is taken somewhere in between Sheffield and Manchester, up in the Peak District. Not today. There is no snow. So here's the plan for this seminar. So there are three main topics which I'll cover. Feel free to interrupt me if I end up going too much over time. So the first thing I'll talk about is I'll try to convince you that there is dark matter in the universe, and I'll explain how we know that there is dark matter. So the first part of the seminar is mostly going to be cosmology, to show what fraction of the universe is made of dark matter. Then I'll move on to saying what the role of the Large Hadron Collider could be in finding dark matter, and a little bit about the future of the Large Hadron Collider and beyond that. So the pie chart here shows the distribution of energy in the universe. You probably have seen this already, but if I take all the energy of the universe and characterize by type, about less than 5% of it is ordinary matter, atoms, which is what you and I are made of. And for every gram of ordinary matter, we got 5 grams of what we call dark matter, which is the topic of this seminar. And we have absolutely no idea what populates this green slice of the pie. And then, of course, an even larger contribution has to do with dark energy, which we're not going to talk about today, and it's even something which is even more mysterious. So what I will focus really is how we can prove that there is this dark matter and how we can experimentally measure it at the Large Hadron Collider. So there you go. So just to warm up, a little bit of Physics 101. Let's take the solar system, right? So the solar system has a big mass at the center, the sun, and the planets go around it. We know the orbit is not really circular, but let's make the assumption it's circular for a moment. So simple physics, F = ma, you can calculate the orbital speed of the planets around the sun, and then you plot the orbital speed of the planets around the sun as a function of the distance from the sun. And what you get is this perfect line. So that rotational speed is proportional to 1 over the square root of r, as this formula shows. So this is really Newtonian physics. Very easy, very simple, it works. Now, if I repeat the argument with a galaxy, now let's take a galaxy, so like this one in the picture. This galaxy rotates around its axis, so it's sort of a flat pancake rotating around the axis. We can measure the rotational speed of the galaxy at various points by looking at hydrogen, which is present in the interstellar medium, and then use the Doppler effect to see, we know there is a 21 centimeter spectral line, and we use the Doppler effect to measure the speed, the rotational speed of the hydrogen in the galaxy. Now, what you would expect, now this is not as simple as a solar system because the mass is not all in the center, there is a mass distribution. So you can assume that the mass distribution is where the stars are and you view them. So what you expect here, if you plot the rotational speed as a function of the radius, or distance of the center of the galaxy, this goes up because there is lots of mass at the center. But once you go over the 10 kiloparsec or so, which is the size of this galaxy, what happens is that there is no more matter, visible matter. And so you would expect this to start going down as 1 over square root of r, just like the planets did in the rotational velocity around the sun. So you would expect to see this line here that falls off as you go far away from the galaxy where there are no stars anymore. However, the experimental observation, and this is 1930s, shows that this is not the case. Instead, it goes out flat with radius all the way up where you can actually see spectral line from this hydrogen line. So clearly there is something going on here. Either gravity doesn't work, which is a possibility. Bear in mind, this is a much larger scale than the solar system, or there is more mass than you actually expect. And so the solution, the way we think it is that there is more mass than you actually expect. So the galaxy, like for instance, the Milky Way, if you do a drawing of the Milky Way, so that would look like a flat pancake, which is where all the stars are. We are here, wave, you can see you. And then there is a center of the galaxy, which we're going to talk about in a moment. And so this blue stuff in the pancake is all what we call the visible matter. But on the other hand, there is a lot of other stuff, which we call dark matter, which we can see. And it's all around the galaxy, forming this sort of oval shape around the flat pancake of the galaxy. So the present understanding is that galaxies not only do they have ordinary matter, but they also have a significant fraction of matter that we don't know what it is. And we call dark matter because it's not visible. So it doesn't emit light, and so it's completely dark. Now, since we can't see, I can show you a picture of it. What I can show you is a picture of a simulation that was done as a so-called millennium simulation for those of you who might be more into cosmology. So this was done to simulate the evolution of the universe from the Big Bang onwards. And so what you see here is where the lumps, where the yellow lumps are, is where the galaxies would be. And all these red filaments is what distribution of dark matter is expected from the simulation. So effectively, a simulation of the universe, taking into account a significant number of parameters, will show all the existence of all these pieces of dark matter, which effectively, what the dark matter does is to hold the galaxies together. So without the dark matter, you wouldn't be able to have this glue that holds the galaxies together. So it's some sort of a gravitational glue that is needed to keep the universe together the way it is right now. I'm probably oversimplifying, but hopefully you get the point. Now, the other way to show evidence of dark matter, and I think this is probably more direct evidence of dark matter, is by using gravitational lensing. So gravitational lensing, this picture shows a little bit how it works. So we are here on Earth, and if you observe a galaxy far, far away, now normally the light from the galaxy to the Earth will travel to a straight line. However, we know that if there is some mass in between the Earth and the galaxy that you observe, the light will be deflected. This is general relativity. So we know that the light is deflected by the presence of masses. So the light, instead of traveling straight, will travel along this curved line, like for instance, these orange lines here. And so if you observe the galaxy, rather than seeing the straight in front of you, the image of the galaxy, what you'll see is some distorted image of the galaxy. So if you take a look at the picture, for instance, this picture, what you see, all these sort of tracks here, rather than seeing a clear picture, what you see is this distorted, this aberration that is due to the fact that the matter between you and the galaxy that you're observing acts as a lens. And so this kind of thing that you see through a lens when you are completely out of focus, when you have an aberration. So by using this information, the strips, if you want, that come from the observation of the galaxy behind your lens, you can reconstruct the mass distribution that is in between you and the galaxy. it's a sort of an inverse problem. If you know what the mass is, you can reconstruct what kind of aberration you have, but also the other way around, if you know what kind of aberration you have, you can reconstruct the mass distribution in front of you. And so this was done, for instance, for the bullet cluster. So what I'm looking at here is I'm observing a galaxy, and so there is a gravitational lens in between me and the galaxy that I'm observing. And so this particular observation is a bullet cluster. So these are two galaxies, in effect. They collided, so they went one against the other, so they traveled once against the other. And what the picture shows in red is the distribution of the hot gas from the galaxy. And we can see, we can measure this distribution using the gamma ray emitted by this hot gas here. While in blue, you show the distribution of the mass that is extracted from the gravitational lensing. So as you can imagine, these two galaxies, they've been interacted, collided, and they passed one past the other. And so what happened is that the gas, the hot gas, during the collision interacted, and so there was some inertia, and the gas slowed down, while the dark matter that is non-interacting just carried on as if nothing happened. So effectively, the dark matter went ahead of the luminous matter. Dark matter in blue went ahead of the luminous matter, sort of having the coupling of the luminous stuff from the dark matter stuff. And if you want, this is a clear evidence of the fact that the position of the dark matter that you can get out from the gravitational weighting, gravitational lensing, is different from the position of the luminous matter that is left behind. So this one is one of the most compelling modern evidence of dark matter. I could probably keep talking about cosmology for another hour, but I'm not a cosmologist, so probably I wouldn't be able to give you a very good view of that. So let me move into something a bit more familiar. So let's start talking about particle physics. Now here is how you make the connection from the cosmology. So we have cosmological evidence that dark matter exists. Now, the reason why we immediately move to from the very, very big to the very, very small is because we need to have an explanation of what this dark matter might be. So the simplest way of doing it is say, well, it's just some random rubbish that is left around the universe. This is what you call macho. It could be massive cosmic halo objects, or just could be some dust around the universe, like some brown dwarfs. So just really some stuff that isn't accounted for. Now the reality is that if there was, if this was an explanation, remember that there is 5 times as much dark matter than luminous matter. So that would be really a lot of stuff around the universe that isn't accounted for. So even if you can't see it, then it will be opaque. And so that implies that you won't be able to see galaxies that are several billion light years away. So this isn't really working. So the solution for dark matter is really to expect that it's made of particles. So the first thing to do is to take a look at particle physics. So this is a representation of the known particles of the standard model of particle physics, and see if you can pick one of those that could be a candidate for our dark matter particle. Now, for various reasons, well, first of all, you have to discount all the particles that are charged, because we know that the universe is not charged. So you get rid of the electron, the muon, the tau. Then you discard all the particles that are not stable. Then you discard the photons because you can see them. So eventually you're only left with neutrinos, but neutrinos have very little mass, and so they cannot really account for the dark matter. So really what it is that the standard model does not provide a candidate particle for dark matter. So you have to go and look at something else. And so what we're going to talk about today is these weak interactive massing particles, otherwise said WIMPs, which is sort of just a position with machos. There are people who think axions could be the solutions, but I'm not going to go into axions, but we will talk about WIMPs. So before we move to particle colliders, another quick digression into the field of cosmology. So how do we know what's the fraction of dark matter is in the universe? So I told you, yes, there is dark matter. I show you the galaxies, they have lots of dark matter around because of the rotational curves or because of the bullet cluster. But how do we find out that 25% of the universe energy is dark matter? So as I said, this is really in the area of cosmology. So let's look at the Big Bang. As you know, a Big Bang starts as a very hot plasma about 15 billion years ago. This very hot plasma explodes, and as it explodes, it cools off. So the way a plasma works is that you have some equilibrium between particles on one side of the question and the other side of the question. So one such equilibrium at very high temperature. So this indicates the temperature as kT, so Boltzmann constant multiplied by the temperature is an energy. So it's a way, if you want to measure the temperature of the universe, by saying what is the average energy, average kinetic energy of particles that are in the universe in that epoch. So when it's very, very hot, then you can have an equilibrium of quarks and antiquarks that can produce these mysterious particles, the Chi1 not tilde, which is, if you want, a candidate dark matter particle. But then since they're very hot, they can recombine and give you again a pair of quark-antiquark. As the universe expands, as you know, a hot gas expanding cools off. When it cools off, then it's not going to be hot enough for these particles to recombine into a pair of quark-antiquark. And so as a consequence, what happens is that these particles, they freeze out. Right? You create them, they're not recombining anymore, so they're going to exist in the universe forever. They expand, and so they will be pervasive in the universe pretty much everywhere. So that's really what you want, right? These dark matter particles, they don't interact, they don't decay, they don't do anything, they just exist forever, and they account for a significant fraction of the mass of the universe. Then when you keep cooling off, you have other possible equilibrium situations, but the one that is most relevant is once you reach the temperature, which is below the 13 electron volt, which is the lower energy state of the hydrogen, atom, then this equilibrium between a proton and electron, at a higher temperature, protons and electrons can exist in a plasma. They're not bound together. But when the temperature goes down, they bind together, they create a hydrogen atom, and then you have photons that are emitted by this interaction. So these photons, they cool off again, they expand, and by expanding, their temperature is reduced. And they go and create what is the cosmic microwave background, which I'm sure I heard about that. So you know there is a background, a microwave background, that was observed by accident. I think it was in the 1940s, by someone was just listening to some radio transmission. There was some noise. They couldn't figure out what the noise was. And eventually it turned out that this is, if you want, the remnant, an echo of what the Big Bang produced of these photons floating around. So with a little bit of cosmology, so what you can see is that the temperature of this microwave background has some small fluctuations, order of 10 to the minus 6 Kelvin, if you translate energy into temperature using the Boltzmann constant. So these very small fluctuations which are visible here in this map. So this is a map, a temperature map of the universe around us as a function of the position. So red is a bit hotter, blue is a bit colder. So this distribution is correlated with the asymmetries that there was in the initial Big Bang. So the matter, after the Big Bang started propagating in different directions. So the temperature, it's correlated to what was the temperature distribution and fluctuation of the initial universe a few seconds after the Big Bang. So by studying that, and here requires quite a lot of mathematical manipulation, but what you do is basically a Fourier transform, Fourier analysis of that distribution, and so you can basically plot the multiple distribution for that picture. And so this was done by the Planck experiment. So by studying that, you can fit some of the parameters, and one of the parameters that you fit is the fraction of dark matter in the universe, as well as a fraction of atoms, baryonic matter in the universe, and a fraction of dark energy in the universe. In particular, also, you can fit the fraction of neutrinos, which is less than 0.06%. And so it turns out that by doing this fit here, with a very good precision, you can say that the amount of dark matter is 24% of the total energy of the universe. So this is what we're looking for. So I think it is remarkable that for every 100 grams of matter, there are at least 500 grams of dark matter, or something that I absolutely have no idea what it is. And this is something that is still today a mystery. We still haven't found what it is. And this is really where particle physics goes in order to be able to isolate these particles. So the first way of trying to isolate these dark matter particles is to say, well, the problem with dark matter particles is that they're not visible, they're dark, so by definition you cannot see them, and they don't interact. Now, it's not really but they have a mass, so since they have a mass, then you have a cosmological evidence of them. Now, it's not that they don't really interact. They did interact at some point in the past of the universe because of the equilibrium, as I showed you. So rather than non-interacting, we call them weakly interacting. So they do have a way of interacting with ordinary matter, but that is very, very weak. The probability of interacting is very small. But they're all around us. So one way to detect them is showing here this diagram. So one possible way of interacting, if there is an interaction, as weak as it can be, there is an interaction between the dark matter and ordinary matter. What happens if when a dark matter particle interacts with a matter particle, let's say a quark, then the quarks get kicked out, and you basically see some radiation, some charged particle radiation. So what you do to do that, you take a tank with liquid inside. So this is, for instance, a picture from one of the latest detectors in the US. A tank with full of very purified liquid, and you just see whether there is any radiation coming out of it. Now, the problem with that is that, first of all, you could have radiation coming from the cosmic rays. Now, to avoid that, you go down in a mine, 2,000 meters underground, inside a mine, so you don't have the problem, or at least the problem with cosmic rays is very, very small. But then, of course, you also have the problem that the natural occurring radioactivity, both inside the liquid, which you can solve by having a chemical pure liquid, or inside the cavern, which is a bit more of a problem because you are in a mine, so there is radon and all this kind of radioactive stuff, which you can veto by observing this radiation as it comes towards the detector. So these are very difficult experiments to do. I mean, because of the chemical purity and the fact that you work in 2,000 meters underground. But this is a picture of the LUX detector in the US. This is 350 kilograms of liquid xenon. And there is a new detector, which will be called the LZ, Lux Zeppelin, which will be coming online, I think, next year or the year after next, which is bigger. So being bigger, will have a bigger sensitivity. So what you do with these detectors, you make this nice plot. So what this plot is showing you, as a function of the mass of the weakly interacting particle, the cross-section that could be observed by a detector. And since things have not been observed, every one of these detectors has set a limit. And so if you look at, for instance, the line for LUX, which is this dashed green line, this tells you that if dark matter exists for a mass of, let's say, 100 GeV, the cross-section has to be smaller than whatever you have on the y-axis. So whatever is at the bottom of the line has not been excluded and still can be searched for, and so experimentally searched for. Of course, you get to the point where you have neutrino interactions and that you cannot shield it. So you have neutrino interactions with your matter. And then beyond that point, you really cannot go with these experiments. So this is a way to search for dark matter directly. You have these dark matter particles, they float around, they come around, they hit a nucleon inside a detector, they kick off some radiation, you observe it. And if you observe it, you probably win a Nobel Prize. If you don't, you win a line on this plot. Another way of observing dark matter, and this is a little bit controversial, but I thought I would put it here just for completeness. So if you take the diagram that I showed a couple of slides ago, right? So here, look at this. You have a dark matter particle interacting with a quark and it stays the same, and the quark comes out. So this is the same diagram, just rotated by 90 degrees. So what could happen, and that's what used to happen in the early universe, is that you have a pair of dark matter particles, they annihilate and create a quark-quark pair. So this was a equilibrium reaction that we have in the early universe. Something like this could still happen when it's very hot, like in the center of the galaxy. So you could have this kind of interactions. And then you could have a production of quarks, and eventually quarks they annihilate and they produce photons that can be observed from Earth. This plot here shows the gamma ray distribution as observed by Fermi-Lat satellite. So it's a large array telescope that observes gamma rays in the universe. So when you point it at the galactic center, the expectation is that the distribution of gamma rays is basically the dashed line here at the bottom. So this, I guess, is the difference between the theoretical distribution and the expected distribution. But there is an excess in the range of a few GeV in the gamma rays. So there are more gamma rays coming from the galactic center than you would expect. So some people say that this is actually the interaction, this sort of interaction of dark matter particle producing a pair of bottom quarks, actually, which eventually they produce this excess in gamma rays in the GeV range. Now, as I said, this is a bit controversial. There's clearly a discrepancy, but the galactic center is such a complicated place of the universe that there are black holes and whatnot. So really the fact that there is a radiation and the range of a few GeV in the galactic center shouldn't really surprise much, but could be that this is evidence of dark matter. So this is the end of my cosmology view, if you want. So I'm going to move now to the Large Hadron Collider and say, well, so the other way of observing dark matter is, instead of observing dark matter that exists already, which is what an astronomer would do, we try to produce it. And by the fact that we produce it, then we can measure the properties of dark matter and do the physics related to dark matter. So this is really the way particle physics works. So this is a picture of the ATLAS detector at CERN with Peter Higgs when he visited a few years ago. As you know, the Higgs boson was observed at CERN because it was directly produced at the Large Hadron Collider. So basically what you do at the Large Hadron Collider, you collide in protons. So the collision will happen at the level of the quarks. The quark collisions will produce a pair of dark matter particles. And by the, well, ideally you would like to observe a pair of dark matter particles, but of course you can't because they're not visible. So you'll observe the fact that they're being produced by the fact that you don't see something. It's one of those things that the fact you don't see something means that you have produced something that you cannot see. We'll come back in a second on the way this is experimentally done. So in order to do that, you need a few ingredients. So the first thing is you need a Large Hadron Collider. So if you start digging, so this is a 27-kilometer tunnel. This is an aerial picture taken from above Geneva. So this is the Geneva airport, just to give you a little bit of an idea of the scale. So it's 27 kilometers around. It crosses the border between Switzerland and France. And it's actually, it's not a single machine, it's a collection. I'm not going to go through the details, but it's a collection of accelerators that eventually lead to the Large Hadron Collider, which is where you collide the protons. And the next slide, if it works, should show a video. No, it didn't work. There we go. Right, so this one is showing a video of how protons collide inside the Large Hadron Collider. So you see here, this is the pipe, the 27-kilometer long pipe inside which you have the protons. So here you see a proton. Proton is made of 3 quarks. So this is traveling almost at the speed of light. This is the ATLAS detector, which is approaching. And then if you look carefully on the other side, you'll see another proton coming in. And so the 2 protons collide. And where they collide, they have a lot of energy. So the energy is equal mc squared. So a lot of energy is released into other particles. And these other particles are detected by the detector, in this case, the ATLAS detector, which of course is built right around the collision point. So by studying the properties of this particle coming up of the collision, you can infer what kind of collision you had and how the physics that behind the collision. So the next thing that you do, as I said, there is a collision point. Outside the collision point, you need to build a detector. And so this rather messy slide shows a few pictures of how the ATLAS detector was built. And just to give an idea of the scale of the detector. So this is a person, a normal size human, just to give you a little bit of an idea of the scale of the detector. I'm sure you've seen the pictures of ATLAS already, so I'm not going to go through it. It's easier to understand on a drawing. So again, this is a drawing, this is a scale. So again, there's a couple of regular sized humans here, just to give an idea of the size. So the way the detector works is that you have central part of the detector where you study charged particles going through. They are charged, there is a magnetic field, and so they deflect in the magnetic field, and so you can study the momentum. Then you stop some of the particles in this part that you call a calorimeter, and all the particles that come out are the muons. Muons don't interact much in the calorimeter. There is another magnetic field up here, and by how they bend in the magnetic field, you can study the momentum and energy of the muons. So as you can see, 45 meters, 25 meters, and you probably don't believe that I have one of those in my office. This point is marooned in my office, but that's a scale. It's a Lego version of it. And it's actually on the right scale. So the Lego people are on the right scale, and you might have seen it somewhere. It's kind of handy to show, but it does need a little bit of repair. This has been a couple of years stuck there. And then, of course, what you need is a large collaboration. We were talking before the seminar is how do you work? Well, ATLAS has about 3,000 physicists. And this picture is actually not all of them. I'm somewhere down here, much younger, but I'm somewhere at the bottom on the ground floor. But yeah, you need a lot of people to operate the detector, to run the analysis, etc., etc. What I keep saying, really, the workforce, the people who do the real work and put everything together are usually the graduate students who join us, and they really do a lot of the real work, and enjoy it. Most of them do. So let's go back to dark matter. Right, so dark matter, as I said, what we were trying to do here, we collide quarks together, we produce a pair of dark matter particles. Now, as I said, the main problem is that the dark matter particles, you can't see them. So it doesn't really work to observe something you can't see. So the way you do it is, instead of looking just for a pair of dark matter particles, you look for events where there is another particle emitted here. We call it a gluon. This effectively is observed as a jet of particles coming out of the interaction. So what you really observe in your collision is one jet of particles coming up in one direction and nothing coming else in the opposite direction. Now, since we know the momentum needs to be conserved, events with what we call monojet, with a single jet emitted in one direction, cannot really exist unless there is something against it in the opposite direction to conserve momentum that you cannot observe. And so it could be that you have all these dark matter particles emitted one side of the detector and the jet of particles emitted on the other side of the detector, and then use momentum conservation to reconstruct what the missing particles would be. And so this is what is done here in this plot, in this graph here. So here what I'm showing is that the momentum of the, so these are monojet events. So these are events with only one jet of particles coming out in one direction. So here I measure the momentum of that jet of particle and how often we measure this particular momentum. Sometimes there will be an imbalance which is due to processes that are driven by the standard model. But if you see an excess here, if you see a peak here, which is not justified by the standard model, you say, here it is, I've got something recoiling against my jet. I don't know what it is. I probably have measured, I've observed a dark matter particle. Now, in this plot, what you see is the histogram. The colored histogram is the expectation from the standard model. The points is what we measure. And quite disappointingly, what we measure is in perfect agreement with the standard model, which means that we haven't observed any evidence of dark matter. So this, if you want, is the most direct way of searching for dark matter at the Large Hadron Collider. Basically, you look for dark matter particles that recoil against a jet of particles that is observed. And so by the absence of something recoiling against this jet, you can infer that dark matter particles are produced, or in this particular case, are not produced. And this nice article down here is quite a useful explanation of how this is done. So hopefully at this point, you're not too tired. You have a moment to talk about yet another problem in particle physics, which I'll come back to supersymmetry in a moment, to dark matter in a moment, which is the fine-tuning problem. Now, the fine-tuning problem, I'll try to give an explanation. This is a rather complex problem in quantum field theory, but basically what it is that if you have a particle, let's take a Higgs boson, this is quantum theory, so the particle doesn't exist on its own forever. What this particle can do is, at some point, pop up a pair of particles, in this case, a pair of top quarks, and then absorb them and go back into being its particle itself. Energy conservation is not a problem, because if you do that for a very short period of time, the Heisenberg principle would tell you that you can violate energy conservation as long as it's done for a very small period of time. Delta T, delta E has to be smaller than h bar divided by 2, I think. And so a particle on its own in quantum field theory will not just exist like a marble and mind its own business. We'll keep doing these sort of things, popping up a bubble, like in this picture, and closing the bubble again. So I think I lost the pointer today. Right. So if you do quantum field theory, then what would happen is that the mass of the Higgs will have a correction, and this correction is calculated by this formula here, where lambda is a constant. And what we do normally, we use the Planck scale for this constant here. And so if you do this, what you end up is for a value of the Higgs mass, which is infinity, unless these two numbers, they cancel out to give you what the observed mass of the Higgs boson is, which is 120 GeV. Now, in order for this to cancel, you really have to have a fine-tuning, that's why it's called the fine-tuning problem, of this lambda f parameter, so that the cancellation, so here we're talking about a number which is 10 to the 19, and you want to cancel out to have a number of the order of 10 to the 2. So the tuning of this parameter m0 and lambda f has to be such that you get the right order of magnitude, right? Really what it is that if this is as 19 digits, you really need to have things that are exactly the same for the first 17 digits, so that the difference is this 120 GeV. So it's not really nice. So one solution to this problem is to introduce a new set of particles. And so basically, if you take all the particles on the standard model, just standing in front of the mirror, and you say, well, for each one of these particles, there is a partner, and the partner has the same name of the particle, it just gets an S in front of it, and the particle is indicated with a tilde in front of it. And so for each one of the particles, say, well, fine, there is an electron, there is a superparticle of the electron, which I call the selectron. And the same you do for all other particles. There is a photon, I call it a photino, etc., etc. Now, you double the number of particles, which might seem a little bit silly, but at the end of the day, that's what you did when you introduced, Dirac did it when he introduced the positron. There were some issues in the theory of quantum electrodynamics, and he said, well, let's assume that there is also the same particle as an electron with positive charge, and here comes the positron, and effectively was observed later on. So the idea might sound a bit silly, but it's nothing unusual. This is a solution for the fine-tuning problem, because, as I said, this was the Higgs boson. This is the Higgs boson popping up a pair of top quarks. The same way you could have a Higgs boson popping up a pair of stop quarks. Stop is the partner on the top. So the top diagrams will have a factor which is written this way with a minus lambda f square. The stop one will have a factor which is plus lambda f square. So the eagle dies, I will have noticed that one is minus, one is plus, you add them, you get 0. And so you have an automatic cancellation of these terms. And so you don't longer need a fine tuning. Now, the advantage of supersymmetry is that, first of all, it solves the fine-tuning problem, which is, I hope I convinced you it's a big problem in particle physics. You create a bunch of particles. Now, all these particles, they interact with each other and they decay into each other. And so at some point, there has to be one which is stable. And the one which is stable, which is at the end of the chain, which we call neutralino, is a candidate for dark matter. And of course, you also introduce double the number of particles, which means that particle physicists for the next 50 years would be busy measuring new particles and really happy. So that's a picture of me, I guess, at this point. I should probably replace these pictures a few years ago with my supersymmetric partner, which looks exactly the same with a tilde in front of it. Now, obviously, there are negatives in doing this. For instance, they have many new parameters, and so the theorists are also very busy with that. But there are also some unphysical problems, like the proton would decay, which is not really good. But there are ways around to avoid the proton decay. But I think the worst problem with supersymmetry is that we haven't observed it yet. I've been talking about supersymmetry for over 20 years, and we keep saying that it's around the corner, but we haven't measured it yet. That's the thing, you know, it's really time for rethink sometimes. So, yeah, I'll go quickly here, but I only wanted to show one thing about why supersymmetry enters. One way supersymmetry can enter here is that you could produce at the Large Hadron Collider a pair of particles, or sparticles actually. And so this is something I've been working on for the past few years, so the pair of protons producing a pair of what we call bottom quarks. And this bottom quark is a supersymmetric partner of the bottom quark, will eventually decay into a bottom quark and a neutralino. And so what you observe here is a pair of bottom quarks and some missing momentum due to the fact that you have these neutralinos that you don't observe. So if you observe an excess of missing momentum in events with a pair of bottom quarks, you could say you have a handle into the searches for dark matter, and you have this kind of measurement of dark matter. Now, the joke here, if I slow down a bit, is that the supersymmetric partner of the top is the stop, which probably means that it's about time I stop talking about these things. It works better in real life. So I'm not going to go through this plot in detail, but these are the, well, actually just been published. If you can see here, it's 2021, the archive number. So again, what you do here, you measure quantities that are related to the two bottom quarks that you measure. And if this measurement has an excess of missing momentum, then you would observe something like the dashed line here. The fact that you don't observe events where the dashed line is means that you probably did not observe any missing particles, and so any dark matter candidates. And so you translate this into limits on the y-axis, for instance, is the limit on the mass of the candidate for dark matter that is excluded in this particular model. So this is very model dependent. This is excluded up to a mass of about 600 Jeff. So if this bottom exists, the mass has to be somewhere which is beyond the red line. So I'm not going to spend more time in talking about supersymmetry and how we search for it at LHC, but hopefully this is a bit of a description of how we do things. Right, so I think I'll skip this one, but the only part I want to say is really that supersymmetry is not the only possibility. There are many alternatives that could have the same explanation. I just listed a few. I wonder if you can spot one that is not really, well, it's written the pink elephants are not really new expected particles, and certainly don't explain the fine-tuning nor the dark matter. But supersymmetry is certainly favored at the moment, and Atlas has a quite large group of people, large working group of people looking for supersymmetric particles in the third generation, as I showed earlier, but also in other areas. So I'm getting to the conclusion, so hopefully this wasn't too long. So the question is, okay, fine, we talked about LHC, what next? So first of all, let's say it's only been 10 years. I know 10 years might sound like a good long time, but the Large Hadron Collider starting operating in 2010, well, 2008, plus there was an accident, so we lost a couple of years, but it's been 10 years, and this line here shows how we've been taking data with time, and you can see that the data set, the size of the data set that we're analyzing is increasing with time as we get better at operating the machine, and of course as we run the machine a little bit longer. And likewise, the center of mass energy is also increased. So if you look at this time diagram here, the expectation is that, so we did what we call the run 1 back in the early 2010s. Run 2 was a 4-year duration, 2015, 2018. And then run 3 starting, actually 21 is not really going to work. No one could put COVID into this graph. So it's starting in 2022 and go to 2024. And then we have what we call the high luminosity Large Hadron Collider starting in 27. And basically, we're going to carry on until 2040. So it's way past my retirement date. Well, not way past, but so it's really something that we're going to put forward for the next generation. And we see generation of students coming along, spending a few years with us, and then moving on into something else, or generation of students coming with on and still staying with us as academics or researcher in Atlas. So it's really a generational thing. You should think of it as a facility more than an experiment. So it's unlike experiments that you might build in your lab, in your physics department. This is a facility to which people contribute, and they do their own favorite physics searches. So one of the things that we're doing for the late 2020s is to replace the inner tracker. The problem we have here, so Manchester is certainly involved as well as we are. One of the issues with the inner tracker is that particle radiation damages the tracker, so we have to build a new one. That of course requires quite a lot of effort and time. This is a picture of one of our engineers building the first one, which is going to be replaced in a few years' time. And this just to give an idea, standard units of the barrel of wine, to see how the tracker, this roughly it's a drawing of how the tracker would look like once it's been replaced. So the construction has started, is actually starting. Things are not going as well as we expected, because obviously people are been away from the lab for a while, but construction is now ongoing and to be deployed back in the late 20s. So what's beyond the LHC? So this is really the end of it. So what's interesting, this plot, so this was shown by Nima Arkani-Hamed, famous theorist, a few years ago. And so basically the obvious future is to build a bigger machine. Why stop at the Large Hadron Collider? But what's interesting in this graph here, if you show as a function of the year of start, the main colliders and the center of mass of the collider. So you see back in the 70s, this was a straight line in the log scale, but you can already see the LHCs beyond the straight line. And the next machine, which is called the Future Circular Collider, well, we think is going to exist late in the 2040s, is certainly beyond this line. And the same is the case for machines that collide electron and positron. In fact, there isn't one at the moment, and even if there is new ones, there will be somewhere here beyond the line. So clearly we are slowing down in the production of these machines. The problem is they cost a lot of money, they require a lot of effort, and they're not really easy to build. And so in a sense, collider physics is starting really to become more and more difficult. But if you believe Nima, a bigger machine, the Future Circular Collider, is the way to go. And so this is a picture of the CERN plans for this Future Circular Collider. So now this is the LHC, looks like a small ring compared to the way the FCC would be. It's nice skiing around here, so it sounds like a perfect place to have an experiment. So you can go skiing if the machine doesn't run. So in a sense, really, it's a generational thing, right? So you're building a facility that will be used by your generation and beyond. So in a sense, some people compare it to building a cathedral. Now the cathedral in Florence took more than 100 years to complete. but it's there for our generation to enjoy. So in a sense, it's a long-term planning that is really no longer like building an experiment, but building something that will be used in the future. And that's all. The most important thing really at this point is to look at the data and hope that the data from the LHC will tell us something new. And there is still hope for supersymmetry. So this was made as a prank a few years ago. SUSY is a conference series that there is one every year. So someone think, well, we're still going to be here in 2215 talking about that. Every time you choose a path of action, a multiverse is killed. And then, of course, there is a perpetual conference, people going to conferences throughout the year to talk about supersymmetry, which I think didn't work out very well. And that's it. Hopefully I didn't talk too much.
Brilliant. Thank you very much for that. Really interesting. If everyone could please unmute and we can try and give a virtual round of applause.
Yeah, I think I've just sent an invite out to unmute. I'm not sure if anyone, I don't know if it's worked.
I don't, do we start clapping now or are you going to give us a cue? Because generally I have no idea.
Well, let's
right.
go 3, 2, 1.
Thank you.
Thank you. Trouble with Zoom that I cannot see the chat when I'm sharing. Oh no, I can actually. Yeah, okay.
That's okay. So yeah, so everyone, obviously you can pop questions in the chat and we can read them out. Or you can ask questions yourselves. So if you just unmute yourself and ask a question directly if you like.
All right, if you're all too shy, I'll go first. So I had one about, so I know this might be a bit of an abstract question and I suppose it might be a bit too early to say, but I was wondering maybe about if there could be any sort of applications of dark matter. So maybe not necessarily like, you know, in a machine or something like that, but maybe applying it to other areas of physics, if that's something, or is that not even being considered at the minute?
That's a good question. Who knows, right? Today's frontier of discovery is tomorrow's application. The main problem with dark matter is that we don't know how to detect, let alone collect it.
Yeah.
But yeah, no, I wouldn't know whether any application would be possible. Certainly not to dark matter. Certainly application of the things that you do to search for dark matter, which is really the way we measure our impact of the work we do. But I cannot think of a direct application of dark matter.
So I'm thinking maybe along the lines of like, if, for example, we discovered dark matter and we could prove it, even if we couldn't physically collect it and produce it on a sort of big scale, I'm wondering if the physics we've learned from that might have knock-on effects for other particle physics, or if it's a bit too niche to sort of be used in other things.
Cosmology for a start.
Yeah.
Because clearly cosmology is based on dark matter. Right? Without dark matter, the universe doesn't stick together. So understanding the nature of it might explain why the universe sticks together.
Okay, thank you.
Sorry, just building on that, I did have a question from like early on when you used, again, I'm not a physicist, so a lot of these things are going to be a bit alien to me, but I do try. But earlier you described the concept of dark matter using the Millennium simulation as kind of like it was holding galaxies together from this. So, but if dark matter has a higher precedence in the entire galaxy, in the entirety of existence, if there's more of it, what does that mean when galaxies collide? They have to collide. Some energy or force has to overcome dark matter in order to collide.
Right. So I think I understand what you're asking. So the thing is that dark matter, in all practical aspects, the only way to interact is through gravitation.
Yeah.
Gravity is only attractive unlike the other forces, right, electromagnetism is both attractive and repulsive, and gravity is only attractive.
Okay.
That's why it's so important in holding things together, because it sort of collapses things to smaller scale just because of the gravity pull. And so what you're looking at here is that when you have two clusters of stars, basically galaxies, right, they interact with each other. The interaction between dark matter is only gravitational, and so this will deflect them a bit. By the end of the day, they'll just go through one from the other without any interaction. While a hot gas, they might emit photons, and so there is more friction between the two of them, and so they slow down.
Okay. Okay, but in terms of dark matter, well, at least because we can't observe dark matter, we have no idea what's happening to it as it collides. So in the other models, you were describing how the essentially Large Hadron Collider collides to quarks, and it's the absence of two exact reactions that infer the behavior. So in a collision in space where two galaxies, two celestial bodies are coming together, would it be at all possible to measure an absence from that, or has that already been done, or has it been?
No, because the difference is that a Large Hadron Collider, you produce the dark matter particle.
Whereas this is already pre-existing.
Yeah.
Okay.
Yeah.
All right, thank you. I enjoyed this.
Thank you.
I have a question about what was being discussed in this part of the slide. Was the idea that the dynamics of the collision is different because we have this in a stellar gas that is somewhat interacting, and then you have an additional dark matter gas that which just pass right through each other? I wasn't quite sure what this bullet cluster image was saying.
Right. So the principle is that these are two galaxies. When the two galaxies are far away, the assumption is that the mass distribution is somewhat centered, right? So like two balls. When you collide them, the hot gas will interact with each other. So the consequence, they slow down because of inertia, while the dark matter doesn't interact with each other, and so they don't slow down, and so they carry on at the same speed. So the blue bits, they carry on, while the red bits will slow down.
And does this affect the blue bits? Because can it be shown? Like, is there snapshots of different bullet cluster collisions, and then you can see maybe these red bits spread out a bit more than they should because you've got these dark matter globulars in the edges. If that makes sense. So like if the dark matter's passed straight through and you've got this mass distribution outside the interaction, so outside the collision, you get two bits of mass attracting the gas and pulling it apart. Is that seen? Is that measured?
Yeah, so basically what you see is the gas staying behind. Now, one of the trouble with astronomy is that you can only observe things at one point in time, right? You cannot observe an evolution because the evolution is such a long time scale that, in a million years, yes, you'll observe something else, but in a million years, you won't be here to observe it. So you only have one snapshot. So you can measure the velocity of the gas, and you can see that the velocity of the gas is consistent with the collision having occurred, and then there is additional matter that has gone faster, if you want, than the gas.
Okay, I think I get that. On the gamma rays from the galactic center, just a question about this bump. Is it at all consistent with measurements or lack thereof with terrestrial experiments? So, is it within reason that this bump could be observed? Is the cross-section of mass that we've excluded, does it allow for this, or does it not? Is that measurement that's been done?
It does. Now, I mean, I have to admit, yesterday I was about to click delete on this slide, but then I said, well,
okay,
nice. Right. So it's model dependent, right? So you can tweak the parameters of the model such that it's consistent with the production of bottom pairs. the reality is consistent with many other cosmological models, astronomical, not cosmological models, like it's the center of the galaxy, there is a black hole. So there could be gamma rays emitted by the black hole. So yes, it could be dark matter, but in practice, in fact, if you look at the more recent papers, which I didn't use because the thing was becoming a little bit too dense in terms of stuff that was on the plot. If you look at the more recent papers, which I can dig out, there are at least 4 or 5 different explanations that would have this pattern, including a lot of astronomical explanations.
Okay, I guess my final question is within like all experimental fields. Is there some kind of like standard program that everyone uses when they've done their observations and they all plug in what they've excluded and it plugs it out, or is it just a paper published every year or two telling what the current situation is when it comes to searching for dark matter? Because you've got like 3 different fields, well, 4: cosmology, astrophysics, direct detection, and indirect detection. It seems like there's a lot of measurements going on. Is there like is it constant talk and people constantly check the consistency of these measurements, or is it just done by a paper every now and then?
Well, you usually release your results as they become available. Now, the reason why results become available at a certain point in time is, first of all, you have to finish your data taking. Then you need to ensure the data taking is robust and it did what you would expect to do. And then you have to do your analysis. And before the analysis is released, particularly large collaboration, there is a lot of internal vetting, just to make sure things are correct. And sometimes the vetting doesn't work. If you remember, a few years ago, there was a story of neutrinos traveling faster than the speed of light. Yeah. And that passed the internal collaboration vetting, and eventually they found out what the problem was. So yeah, things are released publicly. And then, of course, before they're released publicly, there are rumors. Yeah, no, there isn't a coherent way. Quite often, important results are released for specific conferences, just because you want to get the headline of having discovered the Higgs boson rather than something else.
Okay.
We've got quite a long question in the chat. If you want to have a look at that, Davide.
I saw that and I started reading it, but then you asked other questions. Oh, the modified gravity. Is it about the modified gravity? Yeah. Right. Yeah. Every time I give this seminar, I get asked this question about the modified gravity. I'm not a cosmologist, so I can't say, but my understanding is that the gravitational lensing is a way to dispute the fact that modified gravity wouldn't work. So it would the modified gravity would certainly work for the galactic angular rotation speed, because if you modify gravity, instead of 1/r², force goes with, just put another term to it, that would fix it, and you wouldn't notice any difference in the terms of the solar system scale, because that's too small. But on the other hand, the gravitational lensing, which again is general relativity, would not survive this argument. But as I said, I'm not a cosmologist, so I can't really elaborate more than this.
Thank you. Do we have any more questions? If not, I've got one. So you mentioned earlier that for supersymmetry to be natural, the bottom and the stop would have to have mass less than 1 TeV. So I guess 2 questions there. Well, just one. So what does it mean, first of all, for supersymmetry to be natural?
Yeah, so for natural, let's see if I've got it somewhere. For natural, I mean that it doesn't require further fine-tuning. Because the reason why I introduced supersymmetry is that you want to avoid the fine-tuning. Then if you introduce a theory with another fine-tuning, then it isn't really good. On the other hand, there are things that are fine-tuned in the universe, like the moon, the distance, the fact that the moon is always facing us is also a result of a fine-tuning. It's a chance of 1 in 1,000. I don't remember the number exactly. So there are reasons why there could be things like fine-tuned. I mean, fine-tuning basically means that the number has to be exact. Like if you type the number like a phone number, and if you get a digit wrong, then the theory doesn't work anymore. Other people say the anthropic principle comes into place and say the reason why you observe this universe is because it's the only one we live in. But in principle, there are so many, the multiverse theory, there are so many other universes with different manifestations. Some of them live, some of them don't live, but we only observe one. So fine-tuning is, in a sense, yes, it's an argument. It's simple and elegant, but it's not necessarily something that needs to happen.
Okay. Is there then, so is there a limit to how much fine-tuning? So say if we found that Spotterman stop would have to be greater than 1 TeV, so you have to do a bit of fine-tuning. Could you keep doing that indefinitely? And if not, when would you stop? And
yeah, when do I stop? There was a picture of a stop sign, wasn't there? Well, I think the reason why there was this joke about the SUSY 2215 conference is that, I mean, people have been talking about supersymmetry since the 70s, and every time they say, "Oh yes, this is the final test for supersymmetry." I remember at the beginning of the LHC, at the beginning of round 1 of the LHC, so back in 2010, people are saying, "Well, we turn on the machine. If we find supersymmetry in the first month, good. Otherwise, it's gone." But then the theories come up with ideas of why it's not gone, and why you can still have regions of the parameter space where supersymmetry can still exist. And I suspect this will go on forever until you find something. And when you find something, it might not be supersymmetry. I mean, from an experimentalist point of view, my hope is really that you do find something that you were not expecting, because at that point it becomes really challenging to figure out what it is. Yeah, it hasn't happened for a while in particle physics, and yeah, hopefully it has to happen at some point.
Thank you.
It's probably just a good point to give a quick mention, just before we carry on with any more questions, if anyone's got any. We've had an announcement, we can announce now that there'll be another seminar in 2 weeks. That's been confirmed this morning, so that'll be good. So you're all welcome to come down. That'll be about quantum physics and entanglement and quantum teleportation, so do make sure to come to that. Has anyone else got any more questions? Okay.
I've got one final one, as a lot of, I'm sure a lot of people in the society, or people who would be watching this, some anyway, would be interested in doing research at CERN or being affiliated with the CERN. Do you have any advice for any undergraduates wanting to do so? And I guess what was your journey like?
Well, the journey usually, one size doesn't fit all, but most of the journey starts with people getting interested as you do. So you started a journey if you want, and then usually people tend to do a project in the 3rd year or 4th year in particle physics, and pretty sure there'll be plenty of projects on offer in Manchester. The real point in which you get involved as a collaboration, certainly in the UK system, is when you do a PhD. So yeah, I would encourage people who are interested in this in the final year to apply for a PhD. Not necessarily in Sheffield, right? There are many other groups, many groups in the UK who work on ATLAS and other particle physics experiments. In fact, people tend to apply for more than one university. So yeah, that's how the journey starts. And then a lot of people at the end of the PhD, and there are statistics somewhere, but I don't have them on the top of my head, but a lot of people at the end of the PhD decide, well, go look for a real job. Some people stay on, as I did. They do a postdoc, and then eventually they end up in a university position.
Oh, brilliant. Thank you very much for that. Okay, it seems like that might be it. In that case, I'll probably stop the recording now.
Yes.